Right, let's get started. So I'm putting this up just so you will ask about the statistics. And you can see average, mode, median. You can get all that information here. So the average, 79, or the median, 85, depending on which statistical analysis you'd like. They're pretty close to being the same. That's generally a good thing. You'd like the standard deviation to be a little bit lower, but yeah, basically, if you don't know statistics, standard deviation just means 70% of the people fall within one standard deviation of the median, and then like 90 something percent follow that. But then you can see, if you look down here, this is the distribution, and you can see there are a lot of high grades, a couple close, and a bunch of low ones for whatever reason. So just wanted to put that up there. Let's move on to whiteboard and let's go over the tests. So the first problem was I gave you a pole zero map, and you had this, this, and then the root locus does this. And I didn't actually have to show the arrows, but you don't really need to, because it starts at a pole and ends at a zero. So you saw that the line going to the left was not stopping, right? It was just continuing. So you had a zero here at s equals infinity. You had a pole here at a zero here at -4. You had a pole at -3. And another pole at -2. So all you have to do to find your open loop transfer function is you subtract, in the numerator, you subtract the finite zeros, and in the denominator, you subtract the finite poles. So you end up with s plus 4 all over s plus 3 times s plus 2. Most people were able to do this one pretty easily. So I don't know if there's any questions or comments on that, but that was the first problem. Second problem, which you had to do at least the basics of a root locus. So we have a transfer function, open loop transfer function, s plus 4. Oops, sorry, I'm looking at the wrong problem. It's not s plus 4, it's s plus 10. All over s plus 7 times s plus 2 times s plus 1. So the very first thing you should do is define the poles and zeros, right? Whenever we're trying to plot a pole zero map, it makes sense to at least define those initial ones. So our zeros, -10, and our p's, -7, -2, and -1. But we know that we always have the same number of poles and zeros. So we have 2 at s equals infinity, which should immediately tell you I have to solve for asymptotes, right? That's the very first thing that you need to be able to think about, is say, I've got to solve for asymptotes. So I'm going to solve for my asymptotes. Remember that R is n minus m, which is an order of the denominator minus the order of the numerator, is going to give me 2. So my first theta is 2 times my first r, right? Because r starts at 0, 1, 2, etc. So we'll go to the 1 minus 1 multiply by 180 over 2. So you have 2 minus 1, right? Which is 2. Oh, sorry. Is it -1 or +1? Let's see. Did I write that down incorrectly? It is +1, not -1. So that's +1. So 2 times 1, 2 plus 1 is 3. 3 halves times 180 degrees is, I shouldn't say 90, 270 degrees. Now I have my theta 2. Remember, it's plus or minus our one value. So that's 2 times minus 1 plus 1 over 2 times 180 degrees. So 2 times minus 1 minus 2, right? Plus 1 minus 1 half times 180 degrees is minus 90. 270 or minus 90 is the same thing, right? So no problem there. Our next asymptote, now we're going to go to our next increment. So 2 times 2 is 4, plus 1 is 5, times 180. What is 5? So that really is equal to 4 over 2 times or plus 1, right? So that's going to be equal to 2 plus 1/2, all multiplied by 180 degrees. 2 times 180 is 720, sorry, 360, which is just 0, right? Because it resets. So realistically, I can just say that that's 1/2 times 180, because when I'm adding 0, essentially doesn't do anything. So that's equal to 90 degrees. And then my last one, theta 4, 2 times minus 2 plus 1 over 2 times 180. So 2 times minus 2, negative 4, plus 1, negative 3. That's equal to minus 270 degrees, which is the same thing over there. So I have my angles of my asymptotes. The only thing I need to do now is figure out where the asymptotes take off. That's the sum of the z's, or the sum of the p's, minus the sum of the z's, divided by n minus m. So that's going to be equal to -7 minus 2 minus 1 minus 10 all over 2. That's equal to 0, isn't it? -7 minus 2, -9 minus 10 plus 10 equals 0. So now what I can start to do is I can start to draw asymptotes, and I know, let me try to draw with a different color here. I know that I get asymptotes that are actually on the j omega axis. So I can actually start to draw my root locus now by putting my poles -1, -2, and -7. I also have a 0 here at -10. So now I start at a pole and end at a 0. Start at a pole and end at a 0. So this locus is complete. These other two need to do something like this, right? Going down in that direction. And so I didn't actually calculate this break-in, breakaway point, because I don't need it exactly, because all I care about is identifying the region where I have a 20% overshoot, as well as a settling time of less than, what did I say, 2 seconds? 10 seconds, sorry. So that means I have my percent overshoot equation, which is equal to 100 e to the minus pi zeta, all divided by pi squared. Nope, it's 1 minus zeta squared. I had that right. 1 minus zeta squared. When you did that, you could solve for zeta as equal to the square root of the natural log of my percent overshoot. And remember, this had to be less than or equal to 25%. So now this becomes the natural log of 0.25 squared divided by pi squared plus the natural log of 0.25 squared. And when I calculated that out, that was 0.404. So that's my value of zeta that it needs to be. Now my omega sub n, right? My omega sub n, it has to be that I want my settling time to be less than 10 seconds. So my settling time is going to be less than or equal to 10, which is going to be less than or equal to 4 divided by omega n zeta. So if I move my omega sub n has to be less than or equal to 4 over 10 zeta. And when I plug that in, I had 0.99. Actually has to be greater than, not less than. Yeah. What's that? This right here? Let me change the color real quick. That's the equation for our 2% settling time. So we looked at second order systems. We developed that equation. Yeah. And so now we know that our omega sub n is going to be the hypotenuse, right? So we would pick that to be 0.99, and we want it to be out in this direction. Has to be greater than 0.99 to meet that 10% settling. So that's the first criteria. The second criteria is this zeta equals 0.44. Well, this angle here is the inverse cosine of zeta. When we calculate the inverse cosine of 0.404, we got 66 or around 66 degrees. And so we know that if we want to be less than, right, we want to have a settling time less, a peak value of less than 25%, our zeta has to be less than that. So it can only live between these two regions. So anything inside here, any of those root locus points that exists would meet those design criteria. So all you had to do was draw a base root locus plot or point or set of points. And then once you had that, then you just marked up the diagram with your value of zeta and omega sub n and the regions that it would work. Okay. Questions on that? So this is a little bit of a combination, right, of some root locus material, but also some second order response, because it's fine to be able to draw the root locus, but we actually have to be able to ascertain or pull out the necessary information we need to be able to show, hey, this meets the design criteria. So what points do I pick? I can pick any of these points here, right? Because we know all these points for that root are going to meet it because they're inside that curve. But it's possible that over here someplace or here someplace, we would not meet the design criteria. So for the root locus that's all the way out and it's on the real axis, that one is within the design constraints. The other one, you have those two root loci that leave the real axis, and those can violate those design criteria. So that's when we have to pick in that shaded region shown. Okay, question on number 2. And I didn't need you to do breakaway points or break-in points. I didn't need you to calculate the J omega axis because I wasn't looking for a full-blown root locus. I was really looking for what plots. So if you just did a rough sketch like I did here, that's perfectly fine. we move on to number 3? Okay. Wake up. Doesn't want to wake up. Uh-oh. There we go. Number 3. So we have an open loop gain equal to 1 over s plus 1 times s plus 2 times s plus 7. And remember, you do root locus only for the open loop gain, not the closed loop gain. So we have to go ahead and start our process over again to draw the root locus. So our step 1 is our z's and our p's. So our zeros, we don't have any finite zeros, but we do have -1, -2, and -7 for the finite poles, which means we have 3 out at infinity. So let's go ahead now, and since we're looking for an exact root locus, let's draw our points and start to define where the root locus lives. We know that it starts at a pole and ends at a 0. So we know it goes there, and it has to leave the real axis. Then we know over here it starts at a pole and ends at a 0. Well, we start at that pole and then we end at one of those infinite 0. So we know that this root locus is all done. This one over here is not done. And since we are leaving the real axis, we have to calculate break-in, breakaway points. We also have to calculate asymptotes and all that good stuff. So let's go ahead and calculate our asymptotes. So our first one, theta 0, is going to be 2 times 0 plus 1 times 180. And n minus m is 3 in this case. So we have 60. Then we have our next theta, which is going to be 2 times 1 plus 1 times 180 over 3, which is going to be equal to 180 degrees, which is good because we know that we're approaching at 180 degrees. And then we only have one more asymptote to calculate because we only have 3 asymptotes. So let's see, 2 times 2 plus 1 over 3 times 180 gives us 300 degrees. So we have asymptotes that go 60 degrees, 180, and 300 degrees. It's going to go up at 60 and down at -60. So we need to calculate where our asymptotes originate from. That's our sigma sub b. That's the sum of the poles minus the sum of the zeros divided by n minus m, which we said is 3. So that's -1 plus -2 plus -7 all over 3. -10 over 3 is 3.33. So that's someplace here. And again, that doesn't have to be where the root locus lives, because that's just the asymptotes. Eventually, in time, you will approach that value, but you don't have to start at that value. So we do one asymptote at +60, one asymptote at -60, and what do you know? Those cross the j omega axis. So now I have to calculate my j omega crossing to get some accuracy, which means I have to do a Routh-Hurwitz to find my auxiliary equation. I also need to calculate the break-in or breakaway points. So let's do my break-in or breakaway points. So our break-in points is the partial of k with respect to s, which is going to be equal to the partial of -1, because there are no zeros, over s plus 1 times s plus 2 times s plus 7, with respect to S. I find it easier to do partial or to do derivatives when you have numerators and denominators to just expand any quadratic equations or polynomials, I should say. So S plus 1 times S plus 2 is S squared plus 3S plus 2. Then we multiply that by S plus 7. That's going to be S cubed, right? S times S squared is S cubed. So 3S times S is 3S squared plus 7S squared is 10S squared. And tell me if I'm going too fast. I'm basically doing a fancy FOIL, right? I'm just foiling the three terms and then adding them together. Now I'm going to go ahead and do my S term. So I've got 2S plus 21S, which is 23S, and then plus 14. So I have to take the partial derivative of this one here. Okay. Which is actually pretty easy to not have any numerator terms because the partial of a constant is 0, right? So that's going to be equal to 0 times the denominator, so it's still 0, minus the derivative of the denominator, 3S squared plus 20S plus 23, times the numerator, all over the denominator squared, which I actually don't care about, because I'm setting that equal to 0. So now I have 3S squared plus 20S plus 23 equal to 0. Now I do the quadratic equation. Negative b plus or minus the square root of b squared minus 4ac all over 2a, so that should be 6. And I can't do that off the top of my head. So let me just go ahead and fire up MATLAB. Unless somebody else has it. You got the numbers? Okay. So negative 1.478. Negative 5.19. Thank you. So I've got two numbers, but I only have one breakaway point as shown here. So the question is, only one of those can be right. Is it negative 1.478 or negative 5.19? Well, to determine which one is correct, the root locus has to leave the real axis at that point. So there has to be a root locus there. Well, at negative 5.19, that's someplace over here. Is there a root locus there? There isn't. So that's not a valid breakaway point. The valid breakaway point is minus 1.478. So we're leaving here. And the only thing we can do now to get any more refinement is to calculate the J omega crossings. To calculate the J omega crossings, we have to find the Ruth Hurwitz, which means we need that characteristic equation, don't we? So the characteristic equation means we need the denominator of the closed loop transfer function. So that's going to be G over 1 plus G times H, right? So G is 1 over S plus 1 times S plus 2, all over 1 plus 1 over S plus 1 times S plus 2 times S plus 7. So we need the denominator. So what we're going to do is do a common denominator. 1 over S plus 1 times S plus 2. I already know what this is multiplied out by, right? Because I needed it to get this right here, right? To be able to do that. So it's S cubed plus 10S squared plus 23s plus 14. Oop. But now don't forget, with my G here in my block diagram, I have a K term. Then I have my G. Oop. And then I have my H. So technically, I need to have a K term over here, don't I? To add that value of gain. So this becomes plus K all over this. When I invert and multiply, I have K times S plus 7 all over S cubed plus 10S squared plus 23S plus 14 plus K. I need the characteristic equation, which means I need this. So now I'm ready to do my Routh-Hurwitz. Here's my S cubed row, S squared, S to the 1, S to the 0. Start putting in my coefficients. 1, 23, 10, 14 plus K. To solve for my S1 term, it's -1 over 10 times the determinant of above. So it's 14 plus K times 1, which is just 14, which is just 14 plus K, minus 230, 10 times 23. And this is the only thing I need to do, because I know that this is 0, right? So I'm going to build my auxiliary equation from here when that goes to 0. So -1 over 10 times K minus 216 has to equal 0, right? Yes, no, maybe. So the 10 and the -1 go away. So K minus 216 have to be equal to 0. So K is going to be equal to 216. That forces that row to go to 0. If you can't see it, if I plug in a positive 216 in here, what ends up inside that parentheses? 0, right? So the -1/10 doesn't affect any of those terms. It just forces it to 0. So now I have this. Now I build my auxiliary equation. 10s squared plus 14 plus K. K is equal to 216. So 10s squared plus 230 is my auxiliary equation. Now I solve for the roots for that. S squared equals -23. So S is plus or minus J square root of 23. So where that crosses is plus J square root of 23 minus J square root of 23. And that's pretty much all you could do to build our root locus. So quite a bit of math, but just the steps, right? Step 1, step 2, step 3, step 4, and on and on and on and on and on until you get your final answer. That's all you needed to do. Any questions on number 3? No, yes? Following along a little bit? All right, let's do number 4. Number 4 was a steady state error equation. And I wanted to solve for an ESS for a unit ramp input, which means ESS for a unit ramp input is either some amplitude over KV. We'll just call it K sub V. And K sub V is going to be equal to the limit as S approaches 0, S times your open loop gain. Your open loop gain here is going to be equal to K over S times JS plus B. The two S terms cancel, and I'm just left with the limit as S approaches 0. K over JS plus B. When S goes to 0, this goes away, so that becomes K over B. That's my velocity constant, not steady state error. Steady state error is here, so ESS is 1 over K over B, B over K. Questions on number 4? All right, let's do number 5. So same thing, we have to calculate ESS for a unit ramp input. So it's 1 over KV. We can look at the open loop transfer function, and we can see it's some value of K, S plus 2, S plus 3, S plus 1. And so we have to even see, is it possible to get steady state error to be equal to 3? Well, this is a type 1 system. And if you remember from your table, a type 1 system is going to give you a fixed error for a unit ramp, right? So we absolutely can do that. So my K sub B term, just like what we did before, my K sub B is equal to the limit as S approaches 0, K over S times S plus 2. Oh, I forgot the S term there. S plus 3, S plus 1. My F's terms will cancel, and then what I'm left with, as I do the limit function, K over 2 times 3 times 1. It's K over 6, right? I want my ESS to be equal to 3, which is 1 over K sub B. Right? So 6 over K has to be equal to 3. So K is equal to 2. So that one you could solve for a gain coefficient to get that. That's it for the test. Questions? What question? Okay, I'll have to take a look. Yeah. Any questions on the test? Fair, not fair?
I didn't realize it was going to be
Well, and I did say, right, one of the problems was being able to calculate some parameters based on steady state performance characteristics. And then we did a lot, if you look at the PowerPoints, we did a lot where we were always looking at, it's the one where we had a plot like this, right? Where we said this was theta, which is the inverse cosine of zeta. And then we talked about this was omega sub d. This was A, and then this was equal to omega. And so, that's the whole thing about root locus, right? Is being able to take these points and convert them to time domain response. So, yeah, at least having the settling time and the overshoot would be pretty helpful for that. Was it harder than you thought? Easier? Okay. A lot of calculations, but the thing that's really cool about the root locus stuff is it gets you to think about what you're trying to accomplish. It's not just plug and chug. you have to think about, do I need to do this or do I not need to do this? And then you can start to, sort of formulate a game plan. So it requires you to just not, hey, I just have to calculate this, this, and this. It's like, well, if I don't have this, I don't need to calculate it. So you can save yourself a lot of steps, as well as a lot of confusion, because it can get confusing. You're like, do I need to do that or not? I'm not sure. So that's why I like doing the root locus stuff. But it kind of caps what we've done for the past almost 8 months, right? Where we're looking at doing Laplace to take everything into the Laplace domain, and then actually being able to do all these calculations. But it was a lot of work going back into the time domain. So as we said, beginning of this semester, we're going to try to live in the Laplace domain as much as we can. So we have calculations of, hey, I want less than 25% overshoot. And I never went and calculated anything in the time domain. I just did it all in the Laplace domain. So it makes your work a lot easier. That's infuriating. Any questions? TV land.
No, my questions are, I guess, focused more on the final. Um, I don't have the other exams to kind of look at and compare as like study notes. Do you turn those back into us? Do you hand them out and I just need to come in and grab them?
Turn in what? The exams?
The exams. If I use exams 1, 2, and 3 to study for the final,
Yeah,
I don't have exams 2 and 3 to kind of review and
you can always stop
use.
by and get those. Yep.
Okay. Okay.
But I will be doing a final exam review next week, and I'll put together one of those final exam review docs. So you can use that. But it won't be as tough as a test because you only have 2 hours, right? We'll do Thursday, we'll do a final exam review. So Tuesday, we'll probably do a little bit more Bodie plot stuff. We'll just do a bunch of practice examples. We'll come up with some stuff and just try to draw it. And we'll create some in class. We'll just be like, hey, let's try this and see if we can build them. We'll go from there. I haven't decided yet. Depends on what we cover on Tuesday. We have covered them, but it was only one class and we went through it pretty quickly. So it just depends if, what we will cover on Tuesday. All right, anything else?
What was the class average, Paul?
Anybody want to say? 79. I put that up at the beginning of class. I think I can still do it here. Let me see. Let me share my screen again. There you go. All right, any other questions? All right, like I said, we'll just do the exam review. So have a great day. I know some of you got to test with me in a little bit, so go study. All right, take care, everyone.